Hi, everybody. My name is Christine Maceo, and I would like to welcome you again to the fifth and final night of the Edwards Air Force Base STEM Educator Workshop for high school educators. I want to thank you for joining us this week, for coming every day at 3:30 after your long school day. And I want to thank Edwards Air Force Base and the Air Force for inviting me to participate in this event. I also want to thank the sponsors of this event, which include the Department of Defense STEM program, as well as the Office of Naval Research and the Naval Academy Foundation, who are the sponsors of the STEM Center at the United States Naval Academy, where I am coming from, in Annapolis, Maryland. So far this week, we've gone through multiple different topics, including optimization and the traveling salesman problem. We looked at cryptography last night, and we also looked at programming and algorithms earlier in this week. And today we're going to look at engineering design, specifically engineering design of rockets. And we are going to start today's session with a little experiment. But before we get to that, I want to pin my workspace over here and just tell you the supplies that you'll need for this activity today. So it's mostly paper-based, so we'll need some paper. I also asked you to get a sheet of cardboard or some thick cardstock, some pens, straws, rulers, and tape. I've got a little flashlight here, so you don't need this tonight, but I wanted to give you some ideas for when you implement this in your classroom. All right, so like I said, we are going to start today with a little experiment. So I would like you, let me move some of the stuff off this paper, this table. I would like you to get out a sheet of paper, again, and just fold it in half because we don't need a whole sheet of paper for this. And cut along that seam. Your scissors. Doesn't have to be straight. And when we do that, we're going to be left with half a sheet of paper, but it's still too much paper for us. So we just want to cut a strip off, maybe 2 or 3 inches wide. And this is what we're going to use for our experiment today. And I'm going to come back to the camera on my face. And the experiment we're going to try first is just to hold it up straight and blow on it. And what happens when we blow on it? Well, the air is coming straight out at it and it's pushing it. So the paper moves in the direction of the air. Okay, so we're going to take that same sheet of paper right here. And we're going to do the same experiment, but we're going to hold it horizontally this time. So we'll hold it horizontally in front of us. Yes, it'll droop a little bit, but we're still keeping it horizontal. You just want to put it under your lips like this. And we're going to make a hypothesis. So we're going to do the same thing. We're going to blow at the paper, blow over the paper, and we're going to make a hypothesis as to which way this paper is going to move when we do that. Is it going to move down? Is it going to just sit there, or is it going to move up? So I'll give you just a few seconds. Maybe somebody wants to type a hypothesis into the chat before we do the experiment. No cheating, no doing the experiment before you type into the chat. Not move it at all. All right, let's see. That's the hypothesis we got. So hold it up sideways like this, and I'll blow over the top. So what happened to that paper? The paper actually raised up as I blew over it. So the hypothesis was not true that it would stay still. Also, you might have thought that it would blow down in the direction of the air like it did when we held it upright. but that also did not happen. So what's going on here? Well, this can all be explained with the scientific principle called Bernoulli's principle. I'm going to put the formula down on this sheet here. Hold on. Formula down here. This is Bernoulli's principle. And what it says, there's a lot of letters in here. So first of all, we are going to cross out this term over here, which has to do with something that doesn't really happen with the air, the fluid that we're in, or at least it can be ignored and still get a pretty precise value here. We have something called P, and this is static pressure. And then we have this term here. So this little thing that looks like a P, it's also actually a rho, refers to density. So it's a constant. And the V over here refers to velocity. So the only two terms that I really care about are the pressure here and the velocity here. And what this basically says is that the pressure in the fluid, in the air, and the velocity of the air sum to a constant. So they sum to a value over here. And that actually means important things for the relationship between pressure and velocity. What it means is that if pressure goes up, velocity has to come down in order for that still to sum to a constant. If pressure goes down, velocity goes up in order to sum to that constant. So when I look at that piece of paper over here, put it back up. And what I'm doing with this piece of paper is I am blowing a stream of air over the top of it. So what I have is high velocity air going across this paper over here. By Bernoulli's principle, that means that the pressure is low up here. There's high or atmospheric pressure down here, lower pressure up here. So there's a pressure gradient. I create a pressure gradient that pushes the paper up. That's the concept of lift. So that's why things fly. So simple experiment, just a piece of paper. And believe me, you won't remember this formula, but you will remember that the paper went up. So I'd like to do one more experiment that also demonstrates that's interesting to watch. And I would like to do that with the other half sheet of paper. So, or the rest of the paper that you have. So I'm gonna make mine a little bit bigger. I'm gonna go with a whole half sheet of paper over here so that we can see and just give you another idea of how to demonstrate or explain Bernoulli's theorem. So this is half a piece of paper again, and I'm going to fold it in half one more time. And I'm just going to put some little feet on it. So just give it a little stand. So what I want to do with this is make a tent. And my tent will stand up better if it's got feet. All right. So you're looking down on the top of the tent. And I want to do a similar type experiment where I put a stream of fast moving air. But this time what I want to do is I'm going to put a stream of fast moving air into the tent. So this is an interesting experiment because when I put that stream of fast moving air into the tent through here, which I'm going to do actually with a straw, if I have the angle of this tent so that the sides are fairly close together, I'm going to create that pressure gradient again because I'm going to have the high velocity air going in here, which creates lower pressure. And then let's see what happens to this tent as I do that. So did you see the sides come together? So I had a really small angle inside my tent. I put a fast moving stream of air into it, and the sides come together. That's because the low pressures on the inside The high pressure is out here and it smushes it together. So same experiment, different angle of the tent. Still going to blow fast moving air in here. And now let's see what happens this time. Flattened out. So same principle, same idea, fast moving air inside, low pressure inside. This time the high pressure is still outside the tent, but it's up here. So pushed it down. So two different ways of looking at Bernoulli's principle. It's a difficult high-level principle to teach, and it's hard to understand, but if you put it in your hands with a piece of paper, then it makes it much more real. And again, that's the principle of lift, and it's why things fly. All right, so that was one concept I wanted to go over tonight. And we're going to need that for our engineering design project. So before we go any further, I do want to go over the engineering design process. And that process includes with, or begins with a problem identification. And then it goes to research. So I'm giving you some basic concepts for research for an engineering design problem that I'm going to ask you to solve later today. So once we start the research, then we're going to start designing, building, testing, and repeating. I haven't told you the actual project we're going to work on today, but this is where we are right now. All right, so the second concept I wanted to talk about today is the center of gravity, or the center of mass. And the center of gravity, or the center of mass, is basically the point on an object where that mass is concentrated. So the average location of the distribution of the mass throughout an object. It's a geometric property of the object, whether it's a regular shape or whether it's in irregular shape, whether it's uniformly distributed or not uniformly distributed. And what I really wanted to go over was a simple mechanical way to determine the center of gravity of any object that's rigid. And so what we want to do is get out the straw that I asked you to bring today. So we are going to investigate the idea of center of gravity with a fairly uniform shape, but one that's easy to analyze, because I don't want to spend a lot of time on it with a more complicated shape today. All right, so to find the center of gravity, all you do is pick up that object and try to balance it. So the center of gravity can be found by the balance point. So this happens to be a very symmetrical and uniformly distributed object, so we'll be able to find it rather easily. But any object you can do this with, anything that you can kind of lean on something and just arrange it and set it up so that it does not fall. So just want it to balance on some kind of edge. I know my finger's a fairly big edge, but this kind of pinpoints the center of gravity right there. I'm going to actually mark that with a Sharpie. Right here. And that's what I will call the center of gravity of the shape like this. And this is probably no surprise to you, so because it is a very uniform shape. It's made of a thin material that's uniformly distributed throughout, and it's symmetrical. So the center of gravity is actually right in the center of this shape. Center of gravity is important when things fly. So we started talking about Bernoulli's principle and how things can lift up in the air. And now I am starting to tell you about the importance of the center of gravity when things fly. So maybe you can get the idea that we're going to build something today that is going to fly. But anyway, center of gravity is important for the study of flight because the translational motion in flight, so the actual movement of an object in flight, can be completely described by the translational motion of that center of gravity. So that's actually where when we're describing a flight path. When something flies, it's actually free to rotate about its center of gravity and not affect the flight path. So if I were to push this forward, I could rotate it about that center of gravity and it's still going in the same exact direction. So we've got 3 different types of rotational motion that can happen around the center of gravity in something in flight. And those are called roll, pitch, and yaw. And so roll is a rolling about the longitudinal axis here. Pitch is a movement in and up and down. And then yaw is rotational this way. So anyway, all of those rotations do not affect the actual movement of the object in the air, but what it does affect is the stability of flight. So we're going to analyze that a little bit later today in our engineering design project. Any questions before I move on? You can feel free to put them in the chat. Anybody? Okay. So then we're going to move on to one more concept that I want to go over. It's actually the most complex concept that we'll be talking about tonight. And it's something called the center of pressure. And the center of pressure is basically where the aerodynamic forces are concentrated on something that flies. So the aerodynamic forces are lift and drag. So we already saw how lift works, and that's the main one that we're going to concentrate on today. But just like the center of gravity or the center of mass is where the mass is concentrated, the center of pressure is where lift is concentrated. And so we're going to look at a simple mechanical way to figure out where that center of pressure is on an object that might be in flight. To pin my workspace again and ask you to get out. And this is the most complex thing I'm going to ask you to do today. I'm going to ask you to get out your piece of cardboard, the straw that we were looking at before for the center of mass, and then some kind of writing instrument and pair of scissors. All right. Again, any questions before we start working on this? All right, so a simple way of figuring out where the center of pressure of an object is to take a look at that pressure, or take a look at that object and put it on something flat. And what you're really looking at is not the 3D object for center of pressure, but you're looking at the shadow of that object or the projection of that object on the surface below. So an easy way to take a look at this might be to put a light right on top of it and cast the shadow. Somebody suggested today to me that I spray paint up here, and the shadow would be what remained unpainted when I looked at that. So that's a great idea too. Maybe even any kind of powder or dust you could do. Now, I picked a cylinder to go over center of pressure with you today because the projection of this is an easy geometric shape to look at. It's actually a rectangle. And so you might even be able to see it if I lift it up, that when I have a shadow on this cylinder, I actually have a rectangle below it. And that rectangle has a width that's the same diameter as the straw and a length that's the same length as the straw. So we can sketch this easily without spray paint and also without a flashlight. But for a more complicated shape, then you can definitely do that. So I'm just going to put the straw on the cardboard here and take out my Sharpie. Oops, got my finger in the way, and draw. I can use the straw itself to help me draw these straight lines, and that would be the shadow of the straw, or the projection of the straw on the paper, on the cardboard. And I want it to be something rigid when I'm looking at center of pressure, because I have to do something with this after I'm done cutting it out. All right, so this is the shadow of the straw on the cardboard, and I'm going to cut it out. And the interesting thing is that once I get this two-dimensional projection of the straw so that I have it out and I can manipulate it, the mechanical way of figuring out where the center of pressure is actually the exact same thing we did with the straw and the center of mass. For the center of pressure, what you want to do is find the balance point for the 2D projection. And I'm actually, it's much easier for me to balance the two-dimensional object on my finger than it was for the three-dimensional object. So if I look at that, I guess it's no surprise also, because of the shape we selected, that the center of pressure is also right at the very center of the projection. It's a symmetrical rectangle, and it's in the same location as the center of mass. So I'm going to mark that on my straw now. I have the center of mass and the center of pressure, and they're at the same location. And you can see it right there. So what does all this mean? So the center of mass and the center of pressure are in the same location on the cylinder. And what does this mean? Well, let's take a look at this. I've got this shape over here. Basically, I have the center of, actually, I could do it up here. Okay, now I've got this rocket or straw right here. Just gave away what we're gonna build. I've got the center of gravity right here. And I've got the center of pressure also right here. So they're in the same location. This is flying through the air. What happens if it runs into some kind of, it's free to rotate, first of all, about its center of mass, so it can rotate as it moves through the flight. Well, let's see what happens when this runs into something that affects its route in flight. So the air is rushing past it, it runs into something, and it just starts to tilt at an angle. So right now I have the center of pressure and the center of gravity acting at that same location. They're going to still act at that same location, and then it's going to sit at this angle. There's nothing to move it back so that it can be in stable flight. So if it hits something again and goes at a different angle, then it's going to fly like this. And there's nothing that's going to right it. There's no restoring force on it. So what this means is this cylinder is actually most happy when it's flying like this. And this is just about as unstable as flight can be. When the center of pressure and the center of gravity are aligned like this, this is called neutrally stable, but it is not aerodynamically stable in flight. These two things have to separate a little bit for there to be forces on it that can move the rocket as it flies and affect its stability. So what happens if the center of pressure, which is up here, is offset and is offset so that it moves in front of the center of gravity? So let's take a look at this again. This is flying through the air, and then there's a force again that throws it off kilter. So it makes it fly at an angle. So now I have the center of gravity that's acting here, the center of pressure that's acting here, and this thing is at an angle like this. So the way these forces are aligned, I've now created a moment. These unbalanced forces actually are creating a torque that will exacerbate that rotation and cause it to rotate even more. Even with a slight disturbance, the forces are forcing it to actually rotate more. So that would not be an ideal situation if I wanted something to fly through the air. So this was neutrally stable and didn't have any forces to correct. This one made it worse. Let's look at our third case, which is when the center of pressure moves behind the center of gravity. This time, if the rocket begins to rotate, I've got the center of pressure pulling this way and the center of gravity pulling this way, and I have a restoring force. So if I get off kilter and rotate a bit about that center of gravity, something's going to restore it down. So if you want this to fly stably, what you want is the center of pressure to be behind the center of gravity. All right, any questions about that? So I just did a lot of research for you on Bernoulli's principle of lift, center of gravity, and center of pressure. And what it is going to relate to is an engineering design project today to design a rocket that will fly in a stable manner. So does that mean it goes the farthest it can go? No, it means that while it's in flight, it continues to fly with stable flight, with a stable flight path. So we are going to take out another sheet of paper and we're going to start some rocket design. Any questions before we do that? All right. So what you need now is another half sheet of paper. And that straw. So you'll need a half sheet of paper and that same straw. Well, it could be a different straw. We're going to cut that half sheet. What we're going to do is make 4 little pieces of paper out of this half sheet of paper. So we'll fold it over twice. Which will give us 4 little folds. And then we will cut along those folds. And we're going to make the bodies of 4 different rockets. And the way these rockets are going to work is they're going to be launched by the straw. So we want the rocket to fit around the straw. So an easy way to do that is to just use the straw as a rolling template. We'll put the rocket in the straw. I'm sorry, we'll put the straw in the paper and we'll kind of roll it up. You don't want it too tight because you don't want it to grab the straw, but you just want to use it as a template, and then tape the seam. Tape the seam. So I like to tape the two ends first and then kind of fill it in the middle. So then when you remove the straw, you will have a template for our rocket body. And we're going to build 4 different rockets today and analyze them in terms of center of pressure and center of mass. So we're going to do that 4 separate times. Hopefully you guys are better paper rollers than I am. I actually am not a very good paper roller. But with practice, yes, we all get better. How's everybody doing with their paper rolling? So I'm halfway done. And we keep rolling. So what I kept constant each time is the diameter. I kept the length and the amount of material constant in these because I only want a couple of variables. I'm doing another experiment. And remember when we did the pendulum earlier this week, we only changed one variable at a time so that when something happened, we could attribute it to the change that we made instead of having too many changes at once and not knowing what was going on. All right, so that was my 3rd one. I have 1 more to do. Maybe you're faster than I am, and maybe you're slower than I am. I can't imagine that you're slower than I am. I really have a hard time with this. There is a reason I'm an electrical engineer. Anybody have any questions about this or have any questions about the building of it or any questions about the engineering design that we're doing? You can feel free to put it in the chat. All right, so I have the 4 bodies of my rocket right now. And each of these is going to turn into a different rocket. We're going to design each of these a little bit differently. And what we're going to study and analyze for each of them is where is the center of mass, where is the center of pressure, and how does this thing fly? All right, so you've got your 4 rockets here. We're going to label them rocket 1, 2, 3, and 4. So rocket 1 is going to be your control rocket. And we'll make that one first. And then we'll talk about what we're going to do with rockets 3 and 4. 2, 3, and 4. All right. Rocket 1 is a control rocket. It's going to just stay a cylindrical shell, just like the straw that we analyzed before. Because we're going to make this a rocket, though, that's going to launch, we have to seal one end so that we can propel it forward. So we're going to take one piece of tape, or however many you need to do it, and we're going to cover one end, seal it up with that tape. So I am, in addition to not being a great roller, I'm also not a great taper. So I'm actually going to put some along the sides here too. What I don't want to do is change the center of mass of this straw, of this cylinder. So I added 2 pieces of tape to the top here to seal off that one side. I want to add the same amount of weight to the other side of the straw, but I don't want to cover that hole up. So I'm going to just take 2 pieces of tape and kind of fit them around the side here where it doesn't affect the hole, but it does balance the weight a little bit. So that's one rocket. Now we're not going to launch them until we're done making all 4 of them, but that's one rocket. We'll call that the control because it's really just a cylinder. All right. Rocket number 2 is going to look at the fact that we want the center of pressure, if the rocket's going this way, to be behind the center of gravity. So right now it's a cylinder, center of pressure and center of gravity are right in the middle. I have 2 choices here. I can move the center of gravity up, or I can move the center of pressure back. So for case number 2, what I'm going to do is move the center of gravity up. So I'm going to separate that center of pressure from the center of gravity by moving the center of gravity up. That means I'm going to add more weight to this side. And what I'm going to do is just cut a few strips of paper here and crumple them up and stuff them in the front. And one strip was not big enough to fit in that diameter. So I'm going to put a few more. So I'm just trying to offset, move that forward a little bit. All right. So I put it in there. And same thing though, I have to seal it up. I have to hold it in place, hold that extra weight in place, plus seal it up. So this time I'm not going to balance the weight of the tape in the back because I actually want more weight in the front. And there's other things you can do. I didn't want to make you buy too much because I was sending you that supply list. But something that works really well for stuffing the front of a rocket are these little earplugs that they give you on the airplane. You can cut off a piece of one of these. They're nice because they squish down so you can really wedge them in, and then they reform. So they make a nice seal. All right, so that was rocket number 2. Rocket number 3 starts out as a cylinder as well. And the center of gravity and the center of pressure are lined up like they were when we analyzed it. This time we're going to take the other route, and we're not going to move the center of gravity up. What we're going to do is move the center of pressure back. And so what we need to do is add lift to the back of the rocket. And if you think about what a rocket looks like in real life, a rocket has something in the back. Anybody want to put in the chat what rockets have in the back? All right, I'm going to tell you. Rockets have fins in the back. So I'm going to add some fins back here. And what fins are doing back there is they're adding lift. So we need about at least 3 fins to add lift to our rocket. 2 is too little. 4 would work also, but we're going to go with 3. And so I had asked you to get a piece of cardstock to bring tonight. And so I'm just going to ask you to chop off 3 corners. Make little triangles. They're right triangles because they're the corner of paper. And these are what we're going to use for our fins. And that will move the center of pressure back by adding the fins. So again, 3 or 4. 4 is easier to space out, but 3 will work just fine. And we're short on time, so we're just going to make 3. Anyway, what you're going to do is cut out those triangles and just tape them to the bottom as evenly as you can. So we're shifting the center of gravity with these fins as well. So that also will move back as we move the center of pressure back. But hopefully we'll be able to keep the center of pressure behind the center of gravity. And again, evenly spaced as much as you can. About a third of the way around each time. Any questions or comments or anything? All right. Got 2 of them on, got 1 left. Right in the middle of the 2 I have. And so you can actually just do this by taping one side of the fin. I think they flop around a little too much, so I'm actually taping both sides. All right, so that's what rocket 3 looks like. It's got fins on the back only. It's got no extra weight up front. It still actually does have a hole up front, so we are going to seal that up as well, because if we're going to launch this, then we need to have this all sealed up. Right, so that is rocket number 3. So we've got rocket number 1, just the cylinder. Rocket number 2 is weighted up front. Rocket number 3 has lift in the back. And rocket number 4 is going to have all of the above. It's going to have fins in the back to move the center of pressure backwards. And it's going to have weight up front to move the center of gravity forwards. So we're going to take just a couple of strips of paper again and stuff them in the front for our extra weight. And then we're going to make a few more fins and tape them to the back. And then we get to the fun part. We're going to launch stuff. First, we're going to make a hypothesis about which one works the best. Then we're going to launch it and see. So I put some paper in the front and I'm going to seal that up with tape. And then I'm going to take my cardstock and cut 3 more triangles out for fins. Tape them to the back, evenly spaced. And you can also, the size of the fin also makes a difference in how these things fly. So these are all parameters that you can change and work on in your classrooms. It doesn't have to all be just what I'm doing today. There's a lot of variations that you can do with this. Usually, I didn't want to make you find it because I don't know how hard it is to find in California, but a lot of times we'll use two size straws, 2 diameters of straws, and we'll actually make the rocket on one straw and use the other one as a launcher. Angle that you launch at also makes a big difference. So you might want to add some geometry into this lesson. You could attach this to a protractor and see how it flies at different angles and whether the design affects how it flies at different angles. Maybe you want the rocket to go straight up instead of straight out, and then you would use a different design than if you want to launch it like a torpedo. So, and it's all just with paper and tape. All right, so that's rocket 4. So again, rocket 1, just the cylinder. Rocket 2, cylinder with extra weight up front. Rocket 3, cylinder with fins on the back. And rocket 4, cylinder with weight up front and fins on the back. Any comments or questions about anything before we do our test? All right, so I'm going to come back over here. And you're not going, I hope you did this with me because you're not going to be able to see since we're remote. I will shoot my rocket at the screen, but I'm not sure that you'll be able to see the differences in the flight paths. But before I launch these 4 rockets at you, what I want to see is, does anybody have any hypothesis that they want to go put into the chat to say which one will fly in the most stable manner? Or the least stable manner? The one with the weight in the front. Okay. All right. So here we go. And again, I'm going to try to shoot it at you. So hopefully you can see what's going on, or maybe I'll shoot it sideways. All right. This is rocket number 1. See if you can see it. So I put the straw in rocket number 1 and I'm going to launch it this way. And when I did it, it tumbled. So it tumbled off screen for you, but what it did is it kind of rolled a little bit. So that was the plain cylinder. This is the one with the weight up front. This is rocket number 2. I'm also going to put it on the straw. This is the one with the crumpled up paper at the front. And when I launch it, it actually went all the way across the room and looked fairly stable, although it did tend to go down a little bit, probably because of that extra weight in the front. This one is rocket number 3. This one's got the fins in the back. So hold on, okay. Rocket number 3. That also was fairly unstable. Actually, that one kind of tumbled a little bit. And actually it got stuck in a computer wire. But before it got stuck in a computer wire, it tumbled. And then this one is rocket number 4. It's got the fins and the weight. And that one went straight. So that one was a stable one for me. Did not go, however, as far as the one without the fins. So I would say for mine, that rocket number 1, the cylinder, and rocket number 3, the one with only the fins, they flew the least stable. Actually, the cylinder itself flew the least stable. The ones that were weighted in the front flew most stably for you. So the hypothesis in the chat about that was right. The one with the fins in the back did not fly as far, but looked straighter in the air when it was flying. So I told you the other one kind of dipped down a little bit. So did anybody get different results than that? You can put it in the chat. All right, so we are going to analyze these rockets. So actually I have another set of all of them right here. We're going to do the same type of analysis actually that we did at the very beginning, where we're going to figure out where the center of pressure is and where the center of gravity is in these rockets and where they lie in relation to each other. So rocket number 1 which was the plain cylinder right here. This was the one that we actually had already analyzed when we looked at the straw. We can reanalyze it now, but to save time, because it's already 7:20, this was a plain old cylinder. The center of mass and the center of gravity both aligned with the center of the rocket itself. Actually, I have those marked. If you balance it on something, you can get the center of mass. And if you look at its shadow, you can get a center of pressure. The shadow is the rectangle that we looked at before. And so actually that's still right in the center. So this was the one where the center of pressure and the center of gravity were completely aligned with each other. And this was the one that flew, when I just launched it, flew in the least stable way. Rocket number 2, so we would not choose that as a rocket design. Rocket number 2 was also a cylinder. So it actually still has the center of pressure right in the center of the shape, because the center of pressure is based on the shadow. And the shadow of the rocket number 1 and rocket number 2 are exactly the same. And they're those, actually, somebody should have written and said you forgot to pin it. Rocket number 1 and rocket number 2 have the exact same shadow, so the center of pressure is in the exact same place. Now the center of gravity for this one we have to test, because this was the one we weighted in the front. And we do that by balancing this, finding the balance point on this. And when I do that, you can see that it isn't in the middle anymore. In the cylinder, it was in the middle. Now it has moved up to the front. So when I look at this, and I actually have these marked with dots right here, the center of gravity is here, the center of pressure is here, the direction of flight is this way. So I've moved the center of gravity in front of the center of pressure. And that's why when I launched this, it flew in a very stable way. One other thing to note is usually you want the difference between the center of pressure and the center of gravity to be substantial enough to be about twice the diameter of the rocket itself. And this looks about 1.5 to 2 times the diameter of that straw. So this was a very stable design. So when that went in the hypothesis, that was a good hypothesis. The other 2, I changed the shape. Right, I added these fins. So these now have a different shadow. So I have to reanalyze the projection of both of these in order to find the center of pressure. And what I did was the exact same thing. So I know we don't have time to do that tonight, but I did the exact same thing. Actually used a flashlight for this one. I put the rocket down on the table and I put the flashlight above it, actually directly above it. And then I just traced the outline of the shape. And the shadow I got has the triangular fins. And remember, this is 3 dimensions. So I didn't push these fins down in the back when I rested it on the table. If they want to be up, then there's a space under here and that I didn't push down. So the fins, the shadow of the fins are actually narrower than if I had smashed it all the way down. But that's what the shadow of that shape looks like. And this is what I want to balance to get the center of pressure for that new design with the fins. So I would balance that on my finger. It's actually fairly close to the fins. Then when I move it over to the shape, you can see that I kind of put a dot right where my finger is. So that's the center of pressure of both of these rockets with the fins on them. Now this is rocket number 3. This is the one without weight in the front. So I know the center of pressure is at that black dot. When I try to find the center of mass by balancing the shape itself, It's actually fairly close to the center of pressure. It's a little bit offset, which is why it flew a little bit better than the cylinder itself, but they're still really close together. It's nowhere near the 1.5 to 2 diameters that I want. So that's why this one continued to tumble. I did manage to move the lift back because my center of pressure is all the way back here, but I also moved my center of gravity back because I didn't balance it with weight up front. And so they still pretty much remained aligned. The final one that we did looked like this. It had fins and it had weight. So we already talked about the center of pressure. When I do the center of mass, or when I find the center of mass for that one, and I find the balance point, I see that it's not near the center of pressure, that it's fairly far removed. In fact, it's about twice the diameter of the straw removed again. And so that's why this one flew in a stable way. It didn't quite fly as far, we said, as the one with just the weight. And that's because it weighs more, right? It has more gravitational force on it. And it's got more drag because where there's lift, there's drag. But in terms of stability, this was the one that flew in the most stable way. So there's a lot, like I said, a lot of other aspects of rocket design and rocket flight that you can study with this. But you have a basic idea of what goes into stable flight now, and you can continue to improve your design. You can try more fins, you can try the launch angle, you can try different sized fins, you can try different sized rockets. So we used half a sheet of paper. What happens if you use a whole sheet of paper? Again, I forgot to pin myself. There. All right. Thinner paper, thicker paper. Like I said, double straws. Launching straight up, launching straight out. And there's lots of engineering design that can go into this, and it has to do with the applications that you want to put on it too. So all of this began with a little bit of research, observation in terms of Bernoulli's principle. And then we looked at several aspects of design that go into rockets, or several principles that apply to rocket flight. And then we turned it into an engineering design project. I will have to warn you that students think that distance is the most important thing. So you'll have to remind them again and again that stability is what we're looking at here, not distance. Any questions or comments or anything about that project or idea? And feel free to put it in the chat. Yeah, actually, there was a comment that it was a fairly complex concept, but interesting to see. So yeah, this is really college level, especially when you get into center of pressure. And it's a really hard concept for even the college students to grasp. So to make it real by touching it, it just makes it more real for them. There's other ways to look at all of these things, but these are the ways that I have found are just the most concrete. They're used to projections. They see it in math class. And so a 2D projection is a nice application of math topics too. So anyway, I hope you did find something of use, or something that you can bring back to your classroom, something that will be of use to you as you head back to your classrooms next week. And I have enjoyed being with you this week every day. And I hope, like I said, that this was of value to you and that you got something out of it. So thank you for inviting me, and have a great school year.
Thanks again, Christine, for being with us all week. I really appreciate all that you've put into this. And thanks to all the people who have participated as well. Hope you guys have a great weekend.
Bye, everybody.